first one last week, and we'll give the third one next week, early next week. I will be recording a lecture on Introduction to Deep Learning as we come into. So this is reinforcement learning part 2. It's actually So this is Reinforcement Learning Lecture 2, the second of at least 3 guest lectures by Vahid Behzadan, who's one of the doctoral students in computer science, who is doing dissertation research in this area. He's graciously agreed to give some guest lectures. You'll see these numbered as lectures, I believe 34, 36, and 38 in the lecture sequence. So I just wanted to point out that I will be uploading, and we will be uploading, and I will be renumbering the actual lectures. These are featured in homeworks 8, 9, and 10, starting with homework 8 that just came out, and it's due early next week. So if you have any questions, please go ahead and address them in Canvas. I've added Vahid as a teacher in the course, and without taking up any more of the hour, please go ahead.
Thank you very much, Bill, and very good morning to you. Well, I see a lot of new faces, which probably means that more than half of you were not here in the past lecture. So I have to do a quick poll to understand where we stand before I begin. How many of you know what dynamic programming is? 1. How many of you know what Bellman Equation is? And how many of you know what MDP stands for? Fantastic. We're going to have fun today. So I did a lecture on the intro to reinforcement learning. The slides should have been uploaded last night. I don't think they are. I'll look into it again and make sure that the slides for the first lecture are on Canvas at most half an hour after this lecture. We're going to do a quick review of the concepts. I don't have much time to go into details of what we covered last time, but in general, we are talking about reinforcement learning. Any guesses what reinforcement learning is about? It can be. In that case, it's called deep reinforcement learning.
Yeah, so I have a question with the reinforcement learning. So that is just a machine learning, or is it deep learning?
Reinforcement learning is a third category of machine learning techniques. We have supervised learning, unsupervised learning, and reinforcement learning. So in the first lecture on RL, I explained how these 3 differ from each other and how they can relate to each other. It's recording now. Thanks for checking. So what does the word remind you of? You've been here. I'm trying to see what others think of it. Reinforcement. What does that mean? Bringing back up? Reinforcement learning is the set of techniques used to learn how to act in an environment. It's a solution or an approach to sequential decision making. We'll do a quick review of what reinforcement learning is about. We'll talk about rewards and returns. We'll talk about environment dynamics, components of a problem, values and action values, optimal policies, Bellman optimality equation, and if time permits, we'll start to look into dynamic programming solutions to reinforcement learning. So for those of us, which is Bill, me, and you who were here last time, this should look familiar. We're talking about an agent interacting with an environment. We're talking about a human being learning to navigate in a new city. We're talking about a robot or a car learning to drive on its own in a new environment. If you want to do supervised learning for this sort of problem, if you want a car to learn on its own to drive around through supervised learning, what you use is imitation learning. Does anyone know what imitation learning is?
So learning by watching another agent perform a task.
That's very true.
Following.
Yeah. So have you covered that topic in this
We
course?
talked about learning by doing, learning by being told. So the sort of flavor of apprenticeship learning. I wrote down the titles. I mainly focused on supervised learning.
Great. So one way to teach a car or an AI how to drive is to show it how a human driver does it. Like we show that the human driver steers right when it comes to a curve to right. And if we want to show how to play the game of Pong or ping pong, table tennis, the supervised learning solution to this problem is to show it how a human being reacts to every situation in the environment. But is that good enough? Does it generalize? What happens if a new state or a new set of circumstances in the environment happens that's not covered in your training set for supervised learning? Well, either your supervised learning was comprehensive enough that it generalizes well to all states, which probably means that you have a very, very, very large training set, or it's going to fail. It's going to do something weird in a new circumstance, in an unseen circumstance. In those cases, when you have a very large state space, when the number of configurations in the space is very large, and we are talking about like real world problems, like driving, which some used to believe is practically an infinite state space because it's very large. Do you know what I mean by state space? It's an early morning lecture, so. Any guesses what an state is? So let's talk about table tennis. I believe that we are all fond of table tennis here, right? How would you represent the game of table tennis or the state of the game? What are the variables that you need? What are the parameters that you need to describe the state of table tennis? Let's make it easier. What are the variables or parameters that you need to describe the state of a game of chess? I agree with you if you say it. Yeah, I see what you mean. You mean pieces. So where the chess pieces are on the grid, on the chessboard, is the state of the game of chess. Like in the very beginning, you have all the pawns on the second row of each side, and then you have other pieces arranged in where they're supposed to be. When a game is played, when a move is made in the game of chess, then the state of the game of chess is changed. Like if the white player, are you all familiar with chess? Not if you're familiar with chess. So it's a board game, and if you make a move in it, you've changed the state. What describes the state? Where each piece on the board is. So state is your representation of the environment. What about autonomous navigation? What can we use to describe the state space in autonomous navigation?
Position of the car on the road, other vehicles on the road, pedestrians.
Yeah.
The state of traffic lights and other traffic controls, possibly other environments such as weather and lighting, time of day.
What about dynamics? Velocity of the car. Would you consider that as a state variable? That is a very good approach. So there are different ways of representing a state. One can be a static representation of the state of the game or the state of the problem that you want to solve, the state of the environment. One can be dynamic. And there are representations of the state space for autonomous navigation that do not include velocity. They include Markovian assumption based on how much the previous state has changed. We've discussed Markov decision processes and what Markovian assumption is and all that in the previous lecture. You can go over either the video lecture or the course slides to learn more about it. So, we are talking about an agent interacting with the environment. The agent observes the state of the environment at time st. Then, the agent performs an action at, sesame, oh, there it is. So, performs an action at, which changes the state of the environment. The environment samples the change state, we call it st+1, state after time t when action at is performed, and it also generates some sort of reward signal. This reward signal in the reinforcement learning is a scalar value, it's a numerical value, and a huge assumption in reinforcement learning is that there's always a reward signal of scalar type, of numeric type, that presents some sort of feedback to the agent. Now, the question is, the problem that you're trying to solve is how to choose these actions, how to choose these actions over time such that the total reward is maximized, or the cumulative reward is maximized. How unclear are things now? I like your answer. Any questions so far? All right, let's move on. So we have a notion of task here. The task is what the RL agent is supposed to do, and RL stands for reinforcement learning. One instance of an RL problem, one problem sets up, like how to play ping pong, how to play the game of chess, how to drive around. That's a task, learning to drive the task. Learning is how should the agent change policy. Do you remember what policy is? I didn't hear that.
Yeah, I mean, what's the policy? Because I didn't come here on the answer.
Yeah. So policy, we'll talk about it in a couple of slides. And the overall goal is to maximize the amount of reward received over time. So we don't care about instantaneous rewards. We don't care about what we get at this very moment. We want to maximize the amount of rewards that we receive over time, like over the horizon of interacting with the environment. A very good example is drinking. I assume that we are all fond of drinking, or were at some point. If you had a drink last night, you would have had fun. If you had a couple of drinks last night, you would have had probably more fun. But this morning, at this very moment, you would be dealing with a huge hangover. That's a huge negative reward. While you had some fun last night, the negative reward that happens in the morning is decreasing the cumulative or the general reward. So again, we're not talking about maximizing instantaneous reward, we're talking about maximizing cumulative or over time reward. So let's dive into a little bit of math. Goals and rewards. Notice that the spelling of the word maximize is British. There are 3 reasons for it. One, this specific slide is from a lecture series presented at the University of Edinburgh. The second reason is this specific problem was designed by a British person. And the third reason is, well, I'm used to typing maximize with an S. So the goal is to maximize total reward received. Immediate reward are, at each time step, is, if you recall, this. This is the immediate reward. We must maximize expected cumulative reward. What do we mean by that? So let's define a new concept called return. And the return is total reward. Like capital RT, we are going to use capital RT from this slide onwards to represent return or total reward. It's going to be the sum of all instantaneous rewards over time. And we can define a final time step. We can define a time horizon represented by tau. And that time step can be infinite. In most cases, in most computational cases, it's not infinite, but it can be infinite. What does it mean that the time step is infinite? What does it mean to solve an optimization problem for eternity?
The agent lives a long time.
Or for eternity. There are very interesting problems that arise if you have an infinite time horizon. We won't go into those details right now, but if you're interested in learning about those problems, you can watch a completely irrelevant movie called A Man from the Earth. It talks about someone who lives forever. But a mathematical problem that arises if you have an infinite time horizon is your RT, your return, can be non-convergent. It can be unbounded. It can go all the way to infinity. One way to bound it is to introduce a discount factor, gamma. So this Greek little thing here is gamma. It's a value between 0 and 1. It can be 0. It also can be 1, but we usually don't go for 1 for the reason that I said. We want to keep the cumulative reward bounded. We want to keep the return bounded. And thus, we reformulate RT by adding this gamma to power of the index of the term as a coefficient. What does this do? What's 0.2 to power 2?
0.04.
Thank you. Guys, bear with me. This is going to get really interesting really soon. Only if you follow what I'm saying. 0.2 to power 2 is 0.04, right? What's 0.2 to power 3? That's true. Do you agree? 0.008. 0.008 is smaller than 0.02. What about 0.2 to power 4? It's smaller than 0.008. So you can see that when you have a number between 0 and 1 and you take it to a positive power, as the power increases, that number decreases. The same holds for gamma. Gamma is between 0 and 1. So let's say gamma is 0.2. Here it's going to be gamma to power 0, 1. So this RT plus 1, the instantaneous reward that you receive at the next time step, is going to remain with or retain its value. Then you have RT plus 2, the reward that is going to be received in the next time step, not the next instant, but the next instant. And we are multiplying it by 0.2, which means that we are giving it less importance. This can mean that we are less certain of that reward, or it can mean that we are, in some sense, we don't care as much about what comes later in time as what's going to happen now. This is how we kind of formulate. The closer to 0 your discount factor is, we call your problem or formulation myopic. Myopic means you only see near future. It's also a medical term and optometric optometrics term, those who wear glasses to see further distances are myopic because we can only see near distances. And then when gamma goes to 1, the agent is farsighted. You care about rewards that come further in time. Any questions so far? Yep. Why is it not variable? Because it makes our formulation easy. You can make gamma variable. This is actually a very good research idea. There are a couple of problems that can use that solution. But the classical formulation of RL uses a constant gamma because it makes life easier. That was a very good question. Thanks for asking. Now, dynamics of the environment. Let's say that we are playing table tennis. You are all familiar with table tennis. Not if you are. Guys, come on. Okay, we are all familiar with table tennis. Let's say that we are playing singles. There's a ball coming towards the right side of the table on my side, and that's the state, that's S. And my action is to do a forehand direct hit. That's A. What's going to happen next? Do I know what's going to happen next? Is the universe predictable? Someone here is nodding no. So you believe that the universe is not predictable.
How can you predict where the ball goes? Right? It depends on your force.
But you adjust your force, right? To achieve a certain outcome. It's because you have some understanding of the physics of the problem. When you train, when you're learning to play table tennis, you know that if I hit the ball at this angle with this amount of force, and if it's coming with a certain force and direction and maybe it curves, if I do that, it will most probably get to that get to a specific point to that opponent's side with a certain force, with a certain angle. This is called the physics of the problem, or the dynamics of the problem. The dynamics of the problem tells you what the transition of a state is like given any action. When you perform an action, you change the state, but what is going to be the next state? That's defined by transition dynamics. You'll learn more about it in the first lecture when you go through it. We talked about this in detail in the first lecture. But you don't always know for sure what the next state is because you don't always have a complete model of the physics of the problem in table tennis, particularly. You have different probabilities assigned to different outcomes. Like I was playing with a very, very powerful, very good player a couple of years ago. And his technique was like whenever the ball hit my bat or racket, it curved. I couldn't really foresee that happening. This is called uncertainty in dynamics. When you are not sure what the dynamics of the environment are, you have to go with a stochastic modeling. And we are all familiar what the word stochastic means, right? Great. So, again, dynamics of the environment is when you choose an action A to implement in situation S or state S, what is the probability of ending up in the state S prime? That's called transition probability, and the notation we use for it is like this. P of going from state S to state S prime through implementing action A is the probability of ST plus 1, the next state, being S prime, given that the current state is S and the current action is A. Clear? Questions? Yeah?
Is it a kind of state diagram kind of thing?
you can go with a decision tree-like or a state diagram-like representation as well. That's actually very helpful in small problems, but not in larger problems. And you know why it's not helpful in larger problems, because it's going to be very difficult to represent a huge state space and action space efficiently. If action A chosen in state S and subsequent state S prime is reached, what's the expected reward? I believe that all of you have done some statistics, right? Are you familiar with the notion of expectation in statistics? So expectation is nothing but weighted average. Weighted average here in this stochastic representation is multiplying the probability of something happening to the value of that thing, and then summing it up. This is equivalent to expectation. So what is the expected reward if we get to S prime? We represent that with this notation, R, S prime, R reward, or expected reward of going from state S to state S prime by implementing action A, So you see this E here, and in many places you'll see an empty E or a shaded E of RT plus 1, given that ST is S, AT is A, and the next state, ST plus 1, is S prime. So what do we need to find out what the expected reward is? What do we need to solve to find out what the expected reward is? What is the necessary knowledge we need to find this out? We need to know transition dynamics, P, and we need to know some notion of the reward function, right? What are we trying to solve here? We are trying to solve for the reward function. If we know the reward function, we already know this. But how can we know the reward function? Do we always know what the reward signal is like? Do we always know what the next reward is going to be? In life, we don't. We estimate it based on our previous expectation or experiences, right? So if you have P and some expected or experience-based model of R, you can come up with this RSS prime A. I know that it must be a little confusing, and it's probably because you haven't read you haven't gone through the first lecture yet. I'm going to try my best. If you have any questions, stop me and ask me. So we talked about RSS prime A. There's another notion that has been traditionally used. You don't really see it in recent literature, but it was there in the first edition of Sutton's reinforcement learning book back in '98, I believe. So RSS prime A is the expected next reward given current state S and action A and next state S prime. There is rho S A, which is the expected next reward given current state S and action A, and it's calculated like this. So what's this P? It's a transition probability. It's the environmental dynamics. What is the probability of going from state S to S prime given action A? Then what is going to be the reward when you get to state S prime by performing action A at state S? And you sum it over all possible S primes. So when you have a stochastic model, you don't necessarily know which state your action is going to take you to, right? If you go to a casino and play jackpot, you don't really know if you pull the lever, whether you'll get all sevens, you'll get the jackpot, or you get different states. You have different possible next states. So when you want to calculate rho, you have to sum this multiplication over all possible next states. And we have to kind of skip this one. We define something called value functions. There's a state value function. Before going through that, we also defined in the last lecture the notion of policy. A policy is a function that maps from state to action. A policy is like religion. It tells you what to do given any state. A policy can be deterministic or it can be a stochastic. If it's deterministic, then it's merely a regular function. It's going to be pi of state S is always going to be in action A. If it's a stochastic, then pi is a probability distribution. So, more formally, policy pi maps states S to probability distribution over actions A. Now, let's define a value of state S, a particular state S, under policy pi, and let's call it V sup pi of S. So what's the value of state S if we are following the policy pi? So what is this value? What does it mean? What kind of value are we looking for? This is the kind of value we are looking for. Expected return starting in S and following policy pi. So let's say that we are in state S. The value of state S is the reward that you get at the next time step, plus the reward that you get at the following time step, plus the reward that you get at the next time step, and all the way to your time horizon, which can be infinite. And all of it is weighted by that gamma factor. Does it make sense? Questions? Why do we need to define this value? Does it have any meaning at all? What does it mean to follow a policy pi? So let's say I have a policy. Let's say that I've trained myself as an RL agent for the task of getting to that door. My policy tells me that if the door is directly in front of you, then take a step forward. I follow my policy for iteration 1. I followed my policy for iteration 2. I followed my policy for iteration 3. For some reason, some noise happened and now I'm slightly deviated from that trajectory. My policy tells me that if the door is to my left, I have to take a step left. So now, the door is in front of me. My policy says that if the door is in front of me, take a step forward. This is what following a policy means. Policy tells you what to do given any state. It's, in a very simplistic sense, a set of if statements. But it's a lot more mathematically beautiful and comprehensive. Instead of discretely describing different states, it can be a mathematical function that tells you what to do given any state. So following a policy pi, if I'm in state S0, I know what my state S1, S2, S3, and all the way to Sn is going to be. So I know what the rewards are going to be. That's how I calculate the value or state value given policy pi. Any questions so far? Now we have state action values, and sometimes abbreviated as action values, Q. You've probably heard the term Q learning, or you might have heard the term deep Q learning. You've heard of AlphaGo if you've been following the AI news. This Q function, or the action value function, is the basis of all of those revolutionary advancements or developments. So the action value, or the Q value, of taking action A in state S under policy pi is Q super pi of SA equals the expected return starting in S, taking A, and then following policy pi. So mathematically, this is how we represent it. It's going to be the expected cumulative reward. Remember, this capital RT is return or total cumulative reward, which is represented by this, given that your initial state is S and the initial action is A. What does this tell you? It tells you how good is taking action A in state S in the grand scheme of things. How good is drinking wine or drinking whiskey the night before an early morning lecture? We probably think of it as not very good, right? So the Q value of drinking whiskey the night before coming to an early morning lecture is low. What about revising the lecture slides from the previous lecture? That's probably a more profitable action to take given the state the night before an early morning lecture. So I hope that this notion is clear. How many of you are CS majors or CS students, computer science students? Cool. 2. How many of you are elec-eng? What's your major? Geography. Yours? Industrial. Operations research? All right. Yours? Okay. And? Agronomy. Cool. So all of you, even in geography, at some point have to deal with dynamic programming. Dynamic programming is a very, very basic and fundamental solution to planning over time or optimizing over time or sequential decision making. And dynamic programming is governed by Bellman formulation, the Bellman equation. I strongly advise you to go and look into what Bellman equation and dynamic programming is as soon as possible. You can actually read it or study it from the textbook, Reinforcement Learning by Sutton. The second edition is already online. It's for free. You don't have to go into too much trouble to get it. Just go on to Google and search Reinforcement Learning, Sutton, second edition. And the first link is going to be the free ebook. Study dynamic programming and Bellman equation. The general idea is through recursion, you're able to optimize for an objective. So to use the Bellman equation and dynamic programming approach, we need to come up with a recursive relationship for V, the state value function. We know that V of S following policy pi is this, right? This is the definition. And this is the following directly from there. But we also know that we can take this RT plus 1 out of this equation. Why? We are beginning at state S. So when you want to solve this summation, what's the very first term? RT plus 1, right? That's how we take it out. And then The rest is the same. If you notice, there is only a +1 difference here. I would really like to solve this on the board, but we are a little behind time. I have to cover at least 20 more slides. This is already in your assignment 8. A very similar problem is already in assignment 8. The idea is you can get from this direct formulation there to this recursive formulation. How is this recursive? We are saying that V pi of state S depends on V pi of the next state. What does V pi of the next state depend on? V pi of the following state, and so on. And this is exactly the Bellman equation. Do you want me to go through the details of this now, or do you want to work on it in your homework?
Yeah, I saw the homework, but it looks like very detailed. Sometimes I don't understand how to do the question.
Yeah. So the second problem, the second oral problem in the homework, I actually haven't seen what other problems have been added to that. The second oral problem is actually using this formulation. Shall we go through this, or shall we cover a few more? It depends on you.
So they have 4 questions. Which question do we need to use in that equation?
This should be the grid wall problem.
The first one?
The first one.
Okay. Actually, we just need to calculate each cell within each.
And then, oh, actually it's the second problem where you have to calculate values with different horizons. Do you remember that? I haven't seen what has gone out. I've just given the problems to Bill. He might have rearranged it. In one of those problems, you're calculating values based on horizon. I'm going to have to move on from this. Getting from the top to the bottom is very easy. I want you to try it on your own in that assignment. You already have the solution here, but try it once to make sure that you get everything. And you can do the same for Q. Do you remember what the difference between Q and V was? Q is action value. V is state value. So here is a recursive formulation of the Q function given policy pi. It's going to be the summation of all possible states that you can end up in if you take action A in state S, given the probability of getting there, multiplied by the reward that results from taking action A to go from state S to S prime, plus the summation over all possible A primes for what happens in the policy, if you follow the policy, with the next Q function. You are at state S prime and you want to take action A prime. Questions? What does it mean? What does this pi S prime A prime mean? What's pi? Policy. So we said that policy only gets S prime as its argument. What does this A prime do here then? What? I can't hear you. Can you? The next step. That's true. A prime is the next action that you take. That's very true. That's a very keen observation. But that's not part of the definition of pi. Remember, pi is a stochastic in many cases. When pi is a stochastic, it's actually a probability distribution, right? So for state S prime, it has a probability assigned to taking each of those possible actions. If the actions possible are A and A prime, let's say, it will give a probability like 0.4 to action A and a probability 0.6 to action A prime. This pi of S prime A prime is actually the probability given to taking action A prime in this policy pi. Okay? All right, so this is actually what you're going to solve in your homework. How can you relate Q to V? before going through this, are Q and V related? Q is state action value, V is a state value. How are these two related? Just in plain words. Well, you can describe the equations, but try to do it in plain words. What does the state value function tell you? How valuable a state is if you follow a policy pi. So if you perform actions based on policy pi, right? What does the Q function tell you, or the Q value tell you? How valuable is taking an action A in a certain state? How can you remove or relate that action to V, or the state value?
So the result of Q is based on V.
How? Using the policy pi. Exactly. So how do we choose actions? What tells us how to choose action? Policy. Policy pi. If you know the policy, you know what action is going to be taken from the next state onwards. What you're doing here in the Q formulation, you're telling it that forget about the policy at this instant. If the policy tells me to take action A prime, I don't really care about it. I want to take action A. Let's assume that we take action A in state S, and then we follow the policy from there onwards. So then we have V of S. V of S is going to be the value of the V of S prime, which is going to be the value of the state resulting from taking action A at state S, because from there onwards we're following the policy. We don't care about the action. The action is given by the policy. And we have this reward return that can result from taking action A. So this is essentially V of S prime plus a reward that can be obtained from taking action A at state S. Is it clear? Doesn't seem like it. So if we were to calculate V instead of Q, what would we do? What would be the action at state S? Exactly. Pi S, right? The action would have been given by pi S. When you talk about QSA, you're assuming that your policy does not necessarily apply to state S. It's going to apply to all other states, all future states, but not in the very first, in the state S that you are looking into. That's where you inject the action A on your own, you calculate possible rewards based on transition probabilities and your model of the return function or the reward function, and from there onwards you assume that everything follows the policy. That's how Q and V are related. And this is essentially the same thing, but the other way around. Now, what's an optimal policy? An optimal policy, pi star, remember this star usually denotes optimality, has the highest, is the policy that has the highest or optimal value function V star. Alternatively, it's the one that follows an optimal Q function or Q star. It chooses the action in each state which will result in the highest return. So if you have a set of policies, if you have a discrete set of policies, and you want to choose the optimal from that discrete set, yeah, What's what?
Reward. Reward.
R-E-W-A-R-D. So reward signal is instantaneous. This reward here is cumulative. Remember, we assume that in reinforcement learning, there is a scalar feedback signal available to tell you how good or how bad you're doing. Like, let's assume that you want to get from point A to point B. Your reward signal could be your distance from point B. And then the cumulative reward is that summation, that weighted summation with gamma that we talked about. Sum of all rewards weighted with gamma over time, over your period of interacting with the environment. If you see lecture 1, there's a much longer discussion on what reward is.
So we can download that kind of slides and
yeah, from Canvas. Okay, so if you have a set of value functions, we are almost over time. If you have a set of value functions, and we want to choose the optimal among those, what do we have to do? We have to find if you have a set of policies and we want to choose the optimal policy, I'm sorry, I apologize. What we do is we find the policy that provides a maximum V of S for all S, right? What about optimal Q? Optimal Q is obtained by the policy which maximizes QSA for all S. I really wish we could go a bit further. Guys, this is really important. If you want to go into machine learning in any sense, in any field of research, knowing what reinforcement learning is about is going to put you at least a head and shoulders above everyone else who claims to be a data scientist or machine learning expert. Read the first 4 chapters from Sutton's book. The title of the book is mentioned in the last slide of lecture 1. Go through lecture 1, go through the first 17 slides of lecture 2. Next time, I don't want to spend much time on reviewing previous material. If you have any questions, ask me before the class. You can probably message me on Slack. You can shoot me an email. Ask me before coming to the class, because next time you have to talk about how to solve the reinforcement learning problem. I only have 3 or at most 4 lectures left, and I really want to talk to you about deep reinforcement learning as well. So next time, come prepared. If there's anything that you're doubtful about, remember, first temple of prayers is always Google. If you can't find the solution there in 10 minutes, email me, find me, or shoot me a message on Canvas. It's important to get the basics before coming to the next lecture. Any questions so far? Yeah, no worries.
With the enforcement limit, so we take some basic idea about we need to know is the policy, reward, and Q value, and the V value, right?
That's true, yeah. Let me see if I can find the previous slides before the next class begins. What's this one?
Yeah, because last week I went to some conference, so I didn't come to this lecture.
I understand how you can get. So here are the slides from the previous lecture. We talked about the difference between reinforcement learning and other types of machine learning. We talked about MDP, or markup decision process. We talked about examples of reinforcement learning. We did at least 5-minute or 10-minute discussion on rewards, major components on RL agent, as you were saying, policy, value, model. We dived into the different definitions of these. We talked about the difference between learning and planning, and we talked about exploration and exploitation. And we almost talked about Bellman Equation and dynamic programming today. Next time, we are going to go over value iteration, policy iteration, Q learning, and the basics of deep reinforcement learning. All right? Thanks for bearing with me, guys.